Okay, I think we're recording. Here we have banked curve notes today. I'm going to set up a little Cartesian grid here that I can kind of copy paste for the few examples that we'll do. We had talked about a car going around a circular curve on a flat roadway, and we're basically taking that same example and then putting the car on an incline. This is an example of like a velodrome. If you drive down Perkins, right by Kenilworth, there's a velodrome there by the park, which is traditionally for bicycles, and it's at a slight incline. Another example would be most large banked curves on interstates will have an incline, so that the friction between the tires and the road is kind of helping to produce the centripetal force, and that tends to be safer because you can not slip as easily if you increase your velocity in the car. So I'm just going to copy this real quick. Right, here's my y-axis, here's my x-axis. So the last example we had of just the car going around a curve on a flat road was car. There are the wheels, there's the top of the car, and my brake lights are in the back. Okay, and the car is traveling this way around the curve. We got the profile view. The overhead view would be, right, there's overhead view of the car. It's traveling with a velocity this way. We're just going to assume that the magnitude of the velocity stays constant. It's just the direction the car is traveling that's changing. And the radial distance, lowercase r, is staying the same. So we have a uniform circular motion where the change in the radial distance is 0. It's staying the same. And when we looked at that, we diagrammed, now back to the profile view of the car, we had a force of gravity Fg equal to the mass of the car times little g. Because it's on a horizontal or flat road, the normal force is equivalent to its weight, so that's the mass of the car times little g. And then we said there must be some force pointing towards the center of this circle, back to the bird's eye view. There's got to be some force there, and we call the net force pointing to the center of the circular motion is the centripetal or center-seeking force. And in the case of the car on a roadway, this is some frictional force. And in order to see what kind of frictional force that is pointing towards the center, you have to think about if the radius is not changing. Look back over to the bird's eye view over here. If the radius is not changing, then look at the direction of the centripetal force. It's perpendicular to the motion of the car, perpendicular to the way the wheels are rolling in the direction of the car. So that's not a kinetic friction, it's a static friction between the wheels and the surface of the road. And it points in the direction of the centripetal force, which is towards the center. And what's relevant to that direction, the motion relevant to that direction pointing towards the center, is a direction along the line of r. And so if the car is not moving relative to the radius, there's no change in the radial distance, then it's not going to be a kinetic friction between the tires and the road that keeps it pointing towards the center or keeps it changing the direction of its velocity. So this frictional force is a static frictional force, F sub s, over there, back to the profile view. And we modified, or we said basically last time when we talked about this, that if the change in radial distance from the center is 0, meaning it has a constant radius as it goes around, then that frictional force is Fs. And then we said, imagine you speed up faster and faster and faster and faster. As you increase in your velocity, since we know centripetal acceleration is v squared over r, and centripetal force equals mass times centripetal acceleration, then the centripetal force varies directly with v squared over r. So if I go faster and faster and keep every other factor the same, then that increasing speed increases the centripetal force. And if the static friction is the only thing providing a centripetal force, then as I increase my speed, I increase the static friction. And at a certain point, that static friction will be broken because it has a maximum. And we know Fs max is equal to mu s times the normal force. And every other static friction value is going to be less than or equal to, every other static friction value is going to be less than mu s times the normal force. At a maximum, it equals mu s times the normal force. So when V max is reached, or as we approach V max, we approach Fs max, but when V max is reached, then Fs max is reached, which is mu s times the normal force. So that's what we'll look at here, just as a reminder. Car's going around, back to the profile view. I have my sigma forces, y direction equals m a y. When I'm looking at the y direction for banked curves or normal curves on flat roads, I'm asking, is the car's height changing at all? No, it's just going around in a circle. So I have a normal force in the positive direction minus my gravitational force equals 0. A normal force equals mg. And we've already drawn those as equal on our free body diagram. So there's the y direction. Then we have in the x direction, sum of the forces in the x equals max, and I can see that static friction is the only thing I have there, and this type of motion, we said there's a circular motion, the velocity is constant, so we're talking about a centripetal force, and the only force there is Fs. It's mv squared over r, and now we're saying, hey, okay, the velocity is reaching a maximum, so when the velocity of this car reaches a maximum, at V max, before it slips and starts to just move in a tangent to that circle, because it no longer has any friction to keep it moving in the circle, so it veers off at a tangent. At V max, we now know Fs max is the static friction. So I have the Fs maximum equals mass times V max speed that it can go squared over r. And we know at a maximum, mu s times the normal force is Fs max. It's mv squared over r. But wait, we know the normal force is mg in our example because it's a flat roadway. Mv squared over r. I'm sorry, these should be v max, okay. My m's cancel. I'm going to solve for v, so v maximum for the flat roadway with friction is going to be, let's go away, mu gr, or mu s r g times square root. There's my maximum speed on a flat roadway. Okay, so we're going to box that, just keep that as an idea to compare to other stuff. Now the banked curve is going to show up. Let's see if I can paste in my grid again. Banked curve is going to show up, and we're going to talk about a banked curve with no friction. So here's my banked curve. Oops. There we go, something like that. It's a pretty steep curve. And I have, okay, it's going to be weird to think of a car. We're going to do a car anyway. I'll give another example in just a sec of something besides a car. But it's doing the same thing. There are brake lights. It's going around this way. Here's the y-axis. And in this example, we're going to have no friction. And we're going to ask, okay, what velocity is necessary to keep the car moving in uniform circular motion on this banked curve, which means I want zero acceleration in the y. I want its height above ground level to stay the same, and I want it to keep traveling in a circle around the banked curve. So that's kind of the question here that'll guide our little investigation. Draw my free body diagram directly on this, because in a moment you might ask, well, how is the car even moving if there's no friction between the tires? Well, you know, good question. Here you could imagine a funnel here maybe that is like a frictionless funnel, a really low friction funnel or something, and you've got something, a particle that's traveling, a piece of dry ice or something, I don't know. It's sliding around inside, traveling along this circular path. It's some height above the base of the funnel. And here's the radial distance, r, to the center of that circle. And you can see that there's some sort of incline there because look, the side of the funnel is at some angle. And I could draw a bunch of these at a lower distance. Right, there's the circle there, and then at a lower distance, the radial distance has changed. And so you can imagine that it's doing a circular path, something like that, but it's at some sort of incline. The normal force on this particle in the funnel is going to be perpendicular to the funnel, right? So there's a normal force. pushing. And there's no friction in this example, but there's still gravitational force acting on it. Those force vectors are not to scale. Just trying to give another example that would maybe make a little more sense when there's no friction. Anyway, back to the car. Let's diagram some forces. We have our Fg, which is equal to mg. That goes straight down. I have a normal force. I'm just going to draw from the center of mass. Normal force right there. And then there's no friction, so that's it. Okay, now with the coordinate system we have set up, this is usually the most convenient way to think of the coordinate system when you talk about a banked curve. That's how it's demonstrated most of the time, is that you make your x-axis parallel to the radial distance. So here's the radial distance to the center, or to the axis of rotation. Rotation is r right there. And so we make that parallel to the x-axis. That usually makes things more convenient. Remember when we talked about resolving forces on an inclined plane, we made the surface of the plane parallel to the x-axis, or rather made the x-axis parallel to the surface of the plane. But we don't have this car sliding up or down the incline. We're just saying, let's keep it at the same height. There's no friction. How fast does it need to be going? So I'm going to need to resolve this normal force into its vertical component right here. There's F normal in the y direction, and then I need to give it a component in the x direction, which is in kind of orange there, F normal x direction. And then the Fg, which equals mg, is just in the negative y direction. Okay, so I'm going to say sum of my forces in the y direction equals ma y. And when I look at that, I see, okay, what do I have in the positive direction? The normal force in the y direction, minus in the negative direction I have gravitational force. And in order to keep the car at the same height, traveling at a constant speed on this thing, there needs to be zero acceleration in the y direction. So that means F normal y direction is mg. Okay, let's break out F equals ma for the x direction. I have, look at my components in the x direction, it's just the normal force. The normal force in the x direction, the orange dotted line, that's the only component of any force that's pointing towards the center of the circle. And this is a centripetal motion, so Fc equals mac. And I'm looking at all the forces pointing towards the center, everything parallel to the x-axis. It's just F normal x direction equals m. And this is v squared over r. And this is the only velocity for which it will maintain this zero acceleration in the y direction. So normal force in the y direction, we need to break out my angle here. So I've got an angle down here in green, theta. And you can imagine that I have this guy drawn again, like we had done before, breaking up the gravitational force component. That's theta. So that's theta. So F normal in the x direction in orange is going to be normal force times the sine of that angle. That's in the x direction. That's over here. I said we were just coming back to the y part there, didn't I? Fn, that's fine. Sine theta equals m v squared over r. And then in the y direction I have F normal in the y direction is the normal force times the cosine of the angle, because it's adjacent, F normal. Cosine theta equals mg. And I want to solve for v, so what am I going to do? I want to take this equation right here, call it equation 1, that's stuff in the x direction. I'm going to divide it by equation 2. So I'm doing 1 divided by equation 2. What's that going to get me? I have F normal sine theta, I'm going to write it all out, equals m v squared over r divided by F normal cosine theta equals mg. And that's going to get me, normals are going to go away. Sine over cosine theta is tangent theta equals, mass is upstairs, it goes away. And then I have v squared over rg. I'm dividing v squared over r divided by g. It's v squared over rg. And then I'm solving for v. So let's rearrange it. And so I've got tangent theta times rg and square root of that. Square root rg tangent theta. All right, so there's a velocity in a banked curve with no friction. No friction. That's the velocity I need to maintain that value. So let's, go back to my funnel, for example. The angle is the same angle the whole time throughout the entire funnel. As you get closer and closer to the bottom of the funnel, your radial distance is getting smaller and smaller and smaller. And that means for every lower height, if it were to maintain its speed there, its velocity would have to increase as its radial distance from the center of the funnel is getting smaller and smaller. That velocity would vary directly with the square root of the radial distance if g and theta are staying the same. Okay, so there's the banked curve with no friction. Now it's time to take it up a notch. Let me see if I'm still recording real quick. Yep, oh, that's 15 minutes already? Oh, geez. Okay. That's fine. We need banked curve now with friction, and there will be 2 examples of it with friction. There's my banked curve in my car again. Let's go, car, let's go. Brake lights. Top. It's going this way. Y-axis, x-axis. Remember, we're always calling towards the center of the circle in these examples. Towards the center of the circle is the positive x direction. Just for convenience, because we have to have a net force towards the center of the circle in order for it to have an acceleration that's centripetal. And this is a circular motion, so it's most convenient usually to call the direction of the acceleration the net acceleration, the direction of the centripetal acceleration, in this case, the positive direction. All right, so here we're going to say there is friction. There is friction. And in this case, if there is friction, I need to draw my forces. I have F sub g, which equals mg. I have my normal force perpendicular to the contact surface. And the question is, oh, well, which way is friction going to go? Well, we're going to look at two possibilities. One, car is about to slide up the incline. And the second example, car is about to slide down the incline. And we're going to look at those extremes because everywhere in between, where it's not about to slide one way or the other, the static frictional force varies, and we don't know exactly what it's going to be. It depends. But if the car's about to slide up the incline, that's our first example that we're starting with. This car's about to slide up the incline. The car's about to go up, that means the friction will be pointing down the incline, and that'll be our static friction. Okay, when we look at the car's about to slide down the incline, then the only thing that's going to change is the direction of the static frictional force will be pointing upwards. Okay, so all we're going to need to do is flip some pluses and minuses. Let's resolve these forces. Normal force, F normal times, there's theta. F normal cosine theta is right there. And then we had orange. I don't really like orange here, but that's okay. F normal sine theta. And now I have to do the same for my static friction. So here's the horizontal component of my static friction. Uh-oh. Where's the angle? Yes, right there, right? Because it would be also right here. And that little dotted green line is parallel to this line. All right, so theta's got to be right there by the car's brake light. And then I have a vertical component of the static friction right here. So that vertical component is Fs sine theta. I see it's opposite my angle. And in orange, I have Fs cosine theta. Okay. Invoke that second law. We're looking at option 1, car's about to slide up. I have sum of the forces in the y direction equals ma y. Let's see what we got in the y direction. In green, I got Fn cosine theta is positive. Fn cosine theta. In the negative direction, so minus, I have Fs sine theta. And I also have mg equals 0. Okay. Got a couple of unknowns there, Fn, Fs. We'll see what we can do with that. Let's look at, let's do it right underneath. Let's do sigma Fx equals max. All right, and this is parallel to our radial distance. So this is all the stuff that's going to add up to be centripetal force. So FC, and let me look in orange, I have normal force. Aha, a portion of the normal force is helping again to generate a centripetal force and acceleration. And now I also have a portion of the static friction, Fs cosine theta, is helping us go up there, equals m, and this is going to be v squared. What kind of v? This is when it's about to slide up. So this is when the velocity is at a maximum, right before it slides up. Right before it slides up the incline, it will have reached a maximum velocity before you go flying off the road. The other way, when the car's about to slide down the incline, is when it's reached its minimum velocity, where it can no longer maintain the current circular motion. There's Vmax squared over r. Okay. Now, these are at a maximum speed. So at Vmax, we have Fs max. It's about to slip. And we know Fs max equals mu s times the normal force. Okay, so we can rewrite this as Fn cosine theta minus mu s times the normal force times sine theta minus mg equals 0. And we can also rewrite this one down here, Fn sine theta plus mu s. I'm getting rid of my Fs, mu s, normal force cosine theta equals m v max squared over r. Okay, so what I want to do is I want to get a value for v max again. That's what I want to see. So I think I'm going to set both of these equations I've found that I'll box in orange real quick. I'm going to set both of these. I'm going to solve for normal force for each one of those equations, and then since they'll both be equal to the same thing, they'll be equal to each other, and that will get rid of normal force, and I think that's the way I want to do it. So I'm going to come over here with this guy. Solving for normal force, I got to add mg, I got to add mu s sine theta, and I got to subtract cosine theta. So here, factoring out normal force is Fn times cosine theta minus mu s sine theta, and then I have minus mg equals 0, and so that's going to become normal force is equal to mg divided by cosine theta minus, yes, good thing I did it that way, I said it wrong, mu s sine theta. Okay, then this guy, when we solve, we got factor out our normal force, we have sine theta plus mu s cosine theta, kind of very similar looking stuff, right? mv max squared over r, and I need to divide, so normal force is going to be equal to m times v max squared divided by r times sine theta plus us cosine theta. Okay, these two guys in green are both equations where Fn is equal to something, so I'll set them equal to one another. So I have mg over cosine theta minus mu s sine theta equals mv max squared over r times sine theta plus mu s cosine theta. And we need to find a way to solve for Vmax. Right away I see my m's are going to be gone. And I'm going to have, I got to get my sine theta plus mu s cosine theta is got to go over there. And I got a g over there. So let's see. I've got, first I'm multiplying my little r by both sides. So that's rg, they're upstairs. And then I've got this piece of work down here is upstairs, sine theta plus us cosine theta, and then that's divided by cosine theta minus us sine theta equals Vmax squared. So we got to take the square root of all this. Oh yeah. Okay, so that's the maximum speed before it starts to slide. Before it starts to slide up the incline. That was condition number 1, or example number 1 there. is going to be this fun stuff, the square root of RG times some fraction. I have sines and cosines and my mu s in there, in that fraction. Look at what it was before. This was no friction, square root RG tangent theta. Now we throw friction in there and we have components of forces doing some action and making a difference. Okay, bear this one in mind. That was about to slide up. Okay, so we're going to have this to compare to condition 2, which, since we've just done this, this will go by much faster. In our free body diagram for condition 2, the only thing that changes is, since the car is about to slide down the incline, where did I put this thing? Right on the x-axis? The car, now symbolized by a dot, is about to slide down the incline, so it's reaching a V minimum before it, or just as it slides down the incline. Right as that's about to happen, we still have our FG. We still have our normal force, the same direction. Whoa, that was weird. Okay, if it doesn't slide down, then the static friction is going to be this way, and we still have the same components for normal force, but now we have a positive component for the static friction. And what do we have in orange? My x component of normal force is still there. That's Fn sine theta. Remember, our theta is here. And then in green, this is Fn cosine theta because it's adjacent. And then I have this component in orange of the static frictional force that now points away from the center of the circle. So that's Fs theta, Fs cosine theta, and I have Fs sine theta, and Fg is Fg. Real quick, this is again condition 2, about to slide down the incline. Second law. Okay, in the y direction, that's green, I have positive Fn cosine theta, positive Fs sine theta, negative Mg equals 0. It's staying at the same height. It's about to slip. X direction, which is our centripetal stuff, is a difference Fn sine theta in the positive direction towards the center of the circle minus Fs cosine theta. We had a plus there before. So all that's changed is pluses and minuses. Equals M, and of course this changes V minimum squared over R. Okay, I'm going to solve both for Fn again. Remember that Fs is at a maximum because it's about to slip, so it's mu s times the normal force. So that gets thrown in there. So for here, we've got my Mg over there, and my Fs has become Fn mu s sine theta. So I have Fn cosine theta plus mu s sine theta equals mg. Solve for normal force. I have mg over cosine theta plus mu s sine theta. Same process as we were doing before. Okay, there's one. Hold on to that. In the x direction, this Fs cosine theta is mu s times the normal force times cosine theta. And we're going to factor out our normal force. And then we have to divide by sine theta minus mu s cosine theta. We've got m v min squared divided by r times sine theta minus mu s cosine theta. Okay. Set those things equal to one another. Equation A, equation B, those are equal to one another. So I've got mg, I'm going to do it in one step, mgr times sine theta minus mu s cosine theta. I just took downstairs and I brought it and multiplied it by what's upstairs over there. And that's going to be equal to, now what's upstairs, mv min squared, mv minimum squared times this fun stuff, and we're going this way, cosine theta plus mu s sine theta. Okay, m's are gone. I have RG, I like to write RG first, I don't know why. Sine theta minus mu s cosine theta over cosine theta plus mu s sine theta equals v min squared, square root. There we go. Excuse me. Okay, magical. Let's take a look. Let's take a look. What did we have over there? I might need to copy paste and look at this on the same page. Oh no, we can see it. Can we? That's probably too tiny on your screen. Let's just take this sucker. This was about to slide down. So that's the minimum speed. Here we go. Paste. Okay, comparison time. Get out of here. Get those lines out of here. Okay. Square root RG up top, about to slide up, is sine theta plus mu s cosine theta. Down here it's become a minus. Downstairs in the top equation, cosine theta minus mu s sine theta. In the bottom equation, downstairs cosine theta plus. Okay, that's the only thing that's changed. All right, so the direction of friction changed. This is about to slide up and about to slide down. We talk about it's about to do stuff because we know that's when it's about to break static friction, and that's when we know this equality Fs at a maximum equals mu s times normal force. Okay, so we can find the value of the velocity. That was Rg tangent theta if there's no friction. There's a minimum and maximum velocity when it's going around a banked curve, if it's about to slide up, if it's about to slide down. I think question number 5, yes, this is the end of this video, but question number 5 in the FRQs, let's just make sure it's the right one. Yeah, this one. A curved road with radius 150 meters is banked at an angle of 25 degrees. Coefficient of static friction is given. Find the speed of the car that does not require any friction force to prevent it from skidding. Find the maximum speed it can reach before sliding up. And then find the minimum speed. And we should have values that are consistent with what we just found in our little derivation there. Okay. So those are our banked curves. We will come back Wednesday. Our activity during early release is our flying pig, so make sure that we've looked at the conical pendulum portion of chapter 6, Newton's forces and other applications.